In 1954, a young graduate student at Princeton University named Hugh Everett III had a problem. He was studying quantum mechanics, the strange and bewildering science of the very small. The dominant idea at the time was called the Copenhagen interpretation, championed by the legendary Niels Bohr. It said that a quantum particle, like an electron, exists in a fuzzy cloud of all possible states at once. This is called a superposition, but the moment you look at it or measure it, this cloud collapses into a single definite reality. The electron is either here or there, not both. This idea of the observer collapsing reality never sat right with Everett. It seemed arbitrary. Why should a conscious observer have such a special role in the universe? It felt messy and incomplete, so he started working on a different idea, a radical one. He went to his PhD advisor, the famous physicist John Archibald Wheeler, and proposed something new. What if the cloud of possibilities, the superposition, never collapses? What if when a measurement happens, reality itself splits? What if for every possible outcome of a quantum event, a whole new universe branches off where that outcome becomes real? In one universe, the electron is here. In another, completely separate universe, the electron is there. Wheeler was initially intrigued, but also deeply skeptical. This was a wild departure from mainstream physics. Everett wrote up his ideas in his PhD thesis in 1957. He called it the relative state formulation, but it would later become known as the many worlds interpretation. He argued that the entire universe, including us, is described by a giant, ever-splitting quantum wave function. There is no special collapse, there are just branches, an almost infinite number of parallel universes splitting apart every fraction of a second for every quantum event everywhere. He traveled to Copenhagen to present his idea to Niels Bohr himself. The meeting was a disaster. Bohr, the patriarch of quantum physics, completely dismissed him. The physics community at large ignored his work. Discouraged and disillusioned, Hugh Everett III left academia. He took a job doing defense analysis for the Pentagon, applying his mathematical skills to Cold War strategy. His revolutionary idea about the nature of reality was mostly forgotten for over a decade. He never returned to physics, but the idea didn't die, it just waited. Number 16, the universe is a patchwork quilt. Our universe is flat. Data from the Wilkinson Microwave Anisotropy Probe, launched in 2001, confirmed this with incredible precision. A flat universe, unlike a curved one shaped like a sphere, is most likely infinite. It just keeps going. The number of ways that particles can be arranged in any given volume of space is gigantic, but it is not infinite. A physicist named Max Tegmark calculated that the number of possible quantum states in a volume the size of our own observable universe, a Hubble volume, is 10 to the power of 10 to the power of 122. Okay? So you have a finite number of arrangements in what is likely an infinite space. This leads to a strange but unavoidable conclusion. If you travel far enough, you will eventually find another region of space with the exact same arrangement of particles as our own. A perfect copy. This is the Level I multiverse, often called the Quilted Multiverse. It's the least exotic type of parallel universe because it requires no new physics. It's just a consequence of big numbers and big spaces. You know, think of it like a deck of cards. There are a lot of ways to shuffle a 52 card deck, but it's a finite number. If you shuffle and deal cards for an eternity, the same sequence of cards will eventually repeat. The universe is the same. The particles are the cards and the laws of physics are the rules of the game. You know, in an infinite space, every possible deal, every possible arrangement of particles must occur. Not just once, but an infinite number of times. This means that somewhere out there, far beyond the reach of our most powerful telescopes, is another region of space identical to ours. In that region, there is another Earth. On that Earth, there is another you. This person is not a ghostly twin or a spiritual counterpart. They are a physical person made of the same atoms, living out the same life. The distance to your nearest identical twin is staggering. Calculations suggest you would have to travel 10 to the power of 10 to the power of 28 meters to find them. That number is so large that writing it out would fill countless books. You could never get there. And it doesn't stop with exact copies. There are also universes that are almost identical. A universe where you wore a blue shirt this morning instead of a red one. A universe where you decided not to read this. A universe where one single atom in your fingertip is in a slightly different position. Every possible variation exists somewhere. This isn't a theory about branching timelines or different dimensions. It's simply about physical space and probability. These other worlds are not parallel to us in some other realm. They are just incredibly far away in our own single infinite universe. We live in one patch of a giant, endless cosmic quilt. We can only see our own patch, the region from which light has had time to reach us since the Big Bang. But the quilt stretches on forever. Number 15, bubbles of reality keep forming. The Big Bang was not a one-time event. The total energy of the universe is thought to be zero, with the positive energy of matter and radiation perfectly balanced by the negative energy of gravity. This means a universe can, in theory, pop into existence from nothing without violating the laws of energy conservation. Our universe may have been born from a quantum fluctuation in a pre-existing void. And if it happened once, it can happen again. This is the core of the second multiverse, often called the inflationary multiverse or the bubble universe theory. It comes from the work of physicists like Alan Guth and Andre Linde, who developed the theory of cosmic inflation in the early 1980s. Inflation theory states that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion, growing from smaller than an atom to larger than a galaxy almost instantly. This theory explains many features of our universe that are otherwise hard to account for, like its flatness and uniform temperature. The theory of eternal inflation takes this one step further. It suggests that this inflationary process never completely stops. While some regions of space-time, like our own universe, slow down their expansion and form stars and galaxies, the wider metaverse, or bulk, continues to inflate at an exponential rate. Within this eternally inflating bulk, new universes are constantly budding off, like bubbles forming in a pot of boiling water. Each bubble is a new Big Bang. Each bubble expands to become its own vast, self-contained universe. What makes this truly mind-melting is that the laws of physics might be different in each bubble. Our universe has a specific set of physical constants: the strength of gravity, the mass of an electron, the speed of light. These values seem finely tuned to allow for the existence of matter, stars, and life. If they were slightly different, the universe would be a sterile, empty place. In the bubble universe model, these constants are not fundamental. They are random outcomes of how each bubble cooled down after its own Big Bang. So there could be an infinite number of other universes all existing within the same larger inflating reality, but each with its own unique physics. Some might be similar to ours, others would be unimaginably alien, universes with 2 dimensions of space instead of 3, universes where gravity is a repulsive force, universes that expand and collapse in a matter of seconds, universes with no matter at all, only radiation. We just happen to live in one of the bubbles where the physical laws were right for life to emerge. This isn't a sign of special design, it's a matter of selection bias. We couldn't exist in any of the other more hostile bubbles, so of course we find ourselves in a comfortable one. This is known as the anthropic principle. We are here because we are here. The other bubbles are just as real, as they are just not our home. Number 14, our universe lives on a giant membrane. In 1999, physicists Lisa Randall and Raman Sundram proposed a radical new model of the universe based on M-theory, an extension of string theory. M-theory suggests that reality has more than the 3 spatial dimensions we experience. It might have 10 or 11 dimensions in total. The reason we don't see these extra dimensions is because our entire universe, everything we know, is confined to a 3-dimensional surface called a brane. A brane is like a giant flat sheet existing within a higher dimensional space called the bulk. This is the Brane Multiverse model. Think of a loaf of sliced bread. Each slice is a universe, a brane. These slices are stacked next to each other in a higher dimensional loaf, the bulk. We are living on one of these slices. We are completely unaware of the other slices, the other brane universes. That might be just a millimeter away from us in a 4th spatial dimension. The particles and forces that make up our reality, like electrons, protons, and the electromagnetic force, are stuck to our brain. They can't leave it. They are like drawings on a piece of paper that cannot leap off the page. But there is one force that might be different: gravity. According to this model, gravity is not confined to our brain. It can leak between the brains, across the bulk. This offers a potential explanation for one of the biggest mysteries in physics, why gravity is so much weaker than the other fundamental forces. It's trillions of times weaker than the electromagnetic force, for instance. The Brane model suggests that gravity seems weak to us because most of its strength is diluted by leaking into the other dimensions and other branes. This idea has some testable consequences. If there are other branes close to ours, their gravitational pull could have subtle effects on the orbits of stars and planets in our own universe. Or high-energy particle collisions, like those at the Large Hadron Collider, could potentially create tiny, short-lived black holes or knock particles off our brain into the bulk, which would be detected as missing energy. So far, no such evidence has been found, but the search continues. The Brane model also offers a new idea for the Big Bang. Instead of a single point exploding, our universe could have been created by the collision of 2 other branes in the bulk. This collision would have released a tremendous amount of energy, creating the matter and radiation of our universe, and setting off its expansion. These collisions could be happening all the time, creating an endless cycle of new universes, where we are just one ripple, one membrane in a vast, higher dimensional ocean. Number 13, quantum choices create new timelines. In 1927, physicists conducted the double-slit experiment. It showed that a single particle, like an electron, behaves as a wave and passes through both of 2 slits at the same time when it's not being observed. But if you place a detector to see which slit it goes through, it suddenly acts like a particle and chooses only one slit. This measurement problem is the central mystery of quantum mechanics. The Copenhagen interpretation said the act of observation forces a choice. But Hugh Everett's many worlds interpretation, which he proposed in 1957, offered a different solution. There is no choice. Both outcomes happen. This is the level of the 3rd multiverse. It's the one most people think of when they hear parallel universe. According to many worlds, every time a quantum event has more than one possible outcome, the universe itself splits into multiple branches. Each branch is a new, separate universe where one of the outcomes becomes reality. When the electron faces the 2 slits, the universe splits. In one universe, it goes through the left slit. In another identical universe, it goes through the right slit. This splitting or decoherence is not a rare event. It is happening constantly everywhere. An unstable atom can either decay or not decay. A photon can either be absorbed by a leaf or reflected. Each of these tiny microscopic events creates a split in the universal wave function. And because we are made of quantum particles, we are splitting too. Right now, as you read this, there is a version of you that just decided to stop reading. There is another version that got up to get a drink of water. There is another that sneezed. Every single possibility, no matter how small, is realized in its own separate universe. These universes do not exist far away in space, like in the Quilted Multiverse. They are all around us, occupying the same space and time, but in a different dimension of reality, completely inaccessible to each other. Once the split happens, the universes can never interact again. They evolve on their own separate paths. The number of these parallel worlds is almost incomprehensibly large, growing exponentially with every passing moment. One of the major criticisms of this theory is its sheer extravagance. It seems to violate Occam's razor, the principle that the simplest explanation is usually the best. Why postulate a near infinite number of unseen universes just to solve a measurement problem? But proponents of many worlds, like physicist David Deutsch, argue that it is actually the simpler theory. It gets rid of the messy, ill-defined concept of wave function collapse and just follows the mathematics of quantum mechanics, the Schrödinger equation, to its logical conclusion. The math works perfectly without any collapse. The splitting universes are just what the equations describe. In this view, our reality is not a single timeline, it's a vast, endlessly branching tree, and we are just living on one of the countless twigs. Number 12, some universes are just better at making life. The fine-tuning of the universe is a genuine puzzle. For example, if the strong nuclear force, which holds atomic nuclei together, were just 0.5% weaker, the element carbon could not form. Without carbon, life as we know it would be impossible. If the cosmological constant, the energy of empty space that drives the universe's accelerated expansion, were much larger, galaxies would have been ripped apart before they could even form. There are dozens of such cosmic coincidences. Why are the laws and constants of our universe so perfectly suited for the existence of conscious observers? One possible answer is the theory of cosmological natural selection, proposed by physicist Lee Smolin in the 1990s. This is a multiverse model that works on the principles of evolution. Smolin suggested that universes are born from the collapse of matter into black holes. When a massive star collapses, it creates a singularity, a point of infinite density. According to Smolin, what happens inside a black hole's event horizon is the creation of a new Bobby universe. This baby universe pinches off from the parent and starts its own Big Bang. The crucial part of the theory is that when a new universe is born, its fundamental physical constants might be slightly different from its parents. They mutate randomly, just like genes in biological evolution. Now, consider which universes will have the most offspring. The answer is the universes that are best at making black holes, because black holes are the mechanism for reproduction. To make a lot of black holes, a universe needs to be able to form massive stars. To form massive stars, a universe needs to have the right physics to create stable atoms, galaxies, and vast clouds of gas. This creates a kind of cosmic evolution. Universes that have physical constants that are good at making black holes will create many baby universes with similar constants. Universes with BOD constants, which can't form stars or galaxies, will not produce any black holes and will therefore have no offspring. They are evolutionary dead ends. Over countless generations of universes, the multiverse will become dominated by universes whose constants are optimized for black hole production. The amazing coincidence is that the conditions needed to make lots of black holes are very similar to the conditions needed for life. You need carbon, oxygen, and other heavy elements which are forged in the hearts of massive stars that eventually become black holes. You need a universe that lasts long enough for stars and planets to form. So, our universe is not special because it was designed for us. It is special because it is a descendant of a long line of universes that were successful at reproducing. The fine-tuning we observe is just a side effect of a universe that is very good at making black holes. We are living in a fertile universe, in a multiverse that favors fertility. Number 11, reality is a projection from a distant surface. In 1997, theoretical physicist Juan Maldacena made a groundbreaking discovery that connected two seemingly unrelated areas of physics. He found a mathematical correspondence between a certain type of string theory in a five-dimensional curved spacetime called anti-de Sitter space and a quantum field theory on the four-dimensional boundary of that space. This is a highly technical result, but its implication is profound and is known as the holographic principle. It suggests that our entire three-dimensional universe might be a projection, like a hologram, of information stored on a two-dimensional surface at the edge of the cosmos. The idea was first proposed by Gerard 't Hooft and Leonard Susskind. They were trying to solve a puzzle related to black holes. According to Stephen Hawking, black holes evaporate over time, and the information about what fell into them is lost forever. This violates a fundamental principle of quantum mechanics, which states that information can never be truly destroyed. The holographic principle offers a solution. It says that all the information about the three-dimensional interior of the black hole is actually encoded on its two-dimensional event horizon, the surface of no return. As the black hole evaporates, the information is not lost, but is released back into the universe from this surface. The principle can be extended to the entire universe. It suggests that everything that happens inside our universe, every particle, every star, every thought you have, is a projection of information stored on a distant two-dimensional boundary, presumably at the cosmological horizon. You can think of it like a television screen. The image on the screen is two-dimensional, but it depicts a three-dimensional world. The information is all on the 2D surface, but we perceive it as a 3D reality. This doesn't mean we are living in a fake, illusory world. The holographic universe would be just as real as the one we experience, but it would mean that reality has a lower dimensional description. The third dimension we experience might be an emergent property, not a fundamental one. The true reality would be the code written on the cosmic boundary. This idea, while highly speculative, is taken seriously by many physicists because it helps to resolve deep conflicts between Einstein's theory of gravity and quantum mechanics. It also sets a fundamental limit on how much information can be contained within a given volume of space. The limit is not determined by the volume itself, but by the area of its surface. This is a strange and counterintuitive result, but it is what the mathematics suggests. If the holographic principle is correct, our universe is just one possible projection. Different arrangements of information on the boundary surface could correspond to different parallel universes, all projected from the same cosmic screen. Number 10, the universe is just one option in a set of all possible maths. In 2003, cosmologist Max Tegmark proposed a final, all-encompassing level of the multiverse, which he called the level the fourth, or the mathematical universe hypothesis. This is perhaps the most abstract and mind-bending of all parallel universe theories. It states that not only are other universes with different physical laws possible, but that any universe described by a self-consistent mathematical structure must exist. In short, all of mathematics is real. The core of this idea is the relationship between physics and mathematics. Physicists don't invent the mathematical equations they use to describe the universe. They discover them. The universe seems to follow mathematical rules with astonishing precision, but why these particular rules? Why the Schrödinger equation or Einstein's field equations? The mathematical universe hypothesis answers this by saying there is nothing special about our set of rules. Every possible set of mathematical rules, every self-consistent structure, describes its own universe. This means there are universes based on mathematical systems completely alien to our own. A universe governed by Euclidean geometry, where parallel lines never meet. A universe where the fundamental objects are not particles, but knots. Or a universe based on cellular automata, like Conway's Game of Life. A universe where the laws of logic are different. If a mathematical structure can be described without leading to a contradiction, then somewhere it exists as a physical reality. This theory tackles the ultimate why question. Why does our universe exist? Because its mathematical structure is one of the possibilities. We live in this one because its particular mathematical structure is complex enough to allow for self-aware substructures like us to emerge and observe it. Tegmark calls this the principle of radical Platonism, the idea that mathematical objects exist in a real physical sense, not just as abstract concepts in our minds. The level the fourth multiverse contains all the other levels. The level I quilted universes are just different starting conditions within the same mathematical structure. The level the second bubble universes are different solutions to the equations of eternal inflation. The level the third many worlds universes are all part of the same quantum mechanical structure. The level the fourth multiverse is the ultimate collection of all possible structures. Of course, this is a deeply philosophical and untestable idea. How could we ever prove the existence of a universe governed by different mathematics? But its appeal lies in its ultimate simplicity and completeness. It removes all arbitrary elements from our description of reality. It suggests that the reason the universe exists and has the properties it does is because it couldn't be any other way. All possibilities are realized. We are just one thought in the mind of the cosmic mathematician. Number 9, our universe is someone else's computer program. In 2003, philosopher Nick Bostrom from the University of Oxford published a paper titled, "Are You Living in a Computer Simulation?" He argued that one of the following 3 propositions must be true. 1. Civilizations almost always go extinct before they develop the technological capacity to create realistic ancestor simulations. 2. Civilizations that do reach this capacity almost always lose interest in running such simulations. Or 3. We are almost certainly living in a computer simulation. This is the simulation hypothesis. The logic is based on probability. If a civilization can create simulations of the past, they would likely create a vast number of them. Think of all the video games and movies we create based on historical periods. A future, technologically advanced civilization could create simulations of their ancestors, us, that are indistinguishable from reality for the beings inside them. The simulated consciousnesses would be just as real as our own. If they run millions of these simulations, then the number of simulated people would vastly outnumber the number of real people in the single base reality. Therefore, if such simulations are possible and common, it is statistically far more likely that we are one of the simulated beings rather than one of the original organic ones. This is a form of a parallel universe theory where other universes are not physically separate, but are different programs running on the same cosmic computer. There could be countless other simulated universes running alongside ours. They could be simulations of different historical periods or of completely different worlds with different physics. Our entire reality, from the laws of quantum mechanics to the speed of light, would just be the parameters of the program. Physicists have considered ways to test this hypothesis. If our universe is a simulation running on a computer, it must have finite computational resources. This might manifest as a grid or pixelation of space-time at the smallest possible scales, the Planck length. Some have suggested looking for glitches in the laws of physics or for evidence that physical constants have changed over time, as if the programmers were patching the code. For example, observations in 2001 of light from distant quasars hinted that the fine structure constant might have been slightly different in the early universe, though these results are highly debated. The idea also raises profound philosophical questions. Who are the simulators? Why are they simulating us? Is it a scientific experiment, a historical research project, or just a form of entertainment? And what happens when they turn the simulation off? The simulation hypothesis suggests that our reality might be nested. Or our simulators might themselves be a simulation created by an even more advanced civilization, a potentially infinite regression of creators and their creations. Number 8. Time is a river with many parallel streams. Einstein's theory of relativity revolutionized our understanding of time. It showed that time is not absolute, but is relative to the observer. It flows at different rates depending on your speed and the strength of the gravitational field you are in. It is woven together with space into a 4-dimensional fabric called spacetime. But a lesser-known consequence of these ideas, combined with quantum mechanics, is the possibility of parallel time streams. This is different from the many worlds interpretation where the universe splits. Instead, it suggests that multiple, distinct timelines can coexist from the beginning. One model for this comes from the Wheeler-DeWitt equation, an attempt from the 1960s to combine general relativity and quantum mechanics. The equation, which tries to describe the wave function of the entire universe, is famously timeless. Time as a variable drops out of the equation entirely. This has led some physicists to suggest that time as we experience it, a linear flow from past to future, is not fundamental, but an emergent property of a deeper, timeless reality. In this view, the universal wave function described by the Wheeler-DeWitt equation contains all possible histories of the universe, all possible timelines simultaneously. These are sometimes called consistent histories. We only experience one of these histories, one stream in the river of time. But other streams exist, just as real, running parallel to our own. These are not branches created by choices. They are complete, self-contained histories of the universe from its beginning to its end. A different approach comes from the idea of closed time-like curves, CTCs. These are pathways in space-time that could, in theory, allow for travel into the past. They are permitted by Einstein's equations, though they would require exotic forms of matter or energy to create. A major problem with time travel is the grandfather paradox. What if you go back in time and prevent your own grandfather from meeting your grandmother? Physicist David Deutsch proposed a solution using a multiverse concept. He argued that if you travel into the past, you don't enter the past of your own timeline. You cross over into a parallel timeline, a different stream. Any changes you make affect that new timeline, leaving your own history intact. This creates a multiverse of coexisting but separate histories. It's a way to resolve the paradoxes of time travel by ensuring that no history can contradict itself. Every journey to the past is simply a move from one parallel time stream to another. While creating a CTC is likely impossible with current technology, the theory suggests that the structure of reality might already include this vast tapestry of parallel histories, ensuring the logical consistency of the cosmos. Number 7 universes are born and reborn in an endless cycle. The Big Bang Theory describes the beginning of our universe, but it says nothing about what came before it. The cyclic universe model, a variation of Brane cosmology, proposes an answer before our Big Bang. There was another universe. This theory, developed by physicists like Paul Steinhardt and Neil Turok in the early 2000s, suggests that our universe is just one phase in an eternal cycle of birth, death, and rebirth. It is sometimes called the ekpyrotic model, from the Greek word for conflagration, or a world-ending fire. In this model, our universe is one of two parallel branes existing in a higher dimension. These two branes are separated by a tiny gap. For trillions of years, the branes are dark, cold, and empty, slowly drifting apart. But a force, sometimes called a dark energy field, eventually pulls them back together. They move towards each other, slowly at first, then accelerating until they collide. This collision is not a violent crash in a single point. It is a gentle contact that happens everywhere on the branes at once. The collision releases a tremendous amount of kinetic energy, which is converted into the hot, dense soup of matter and radiation that we identify as the Big Bang. This event creates a new universe on each brane, and they begin to expand. Our universe is currently in this expansion phase. Over trillions of years, the universe will continue to expand, cool down, and empty out as all the stars die and black holes evaporate. It'll become a vast, featureless void, but the cycle will begin again. The force between the branes will pull them back together for another collision, another Big Bang, another universe. This model offers solutions to several cosmological puzzles without needing the concept of cosmic inflation. For example, it explains the universe's flatness and uniform temperature, because the branes had trillions of years to smooth out before they collided. It also provides a natural explanation for dark energy as the force that drives the cycle. The cyclic universe is a multiverse in time rather than space. There are other universes, but they exist in the past and the future, in previous and future cycles. Each cycle could potentially have slightly different properties, creating a sequence of varied universes. The evidence for this model could lie in the cosmic microwave background radiation, the afterglow of the Big Bang. The model predicts very specific patterns of gravitational waves that are different from those predicted by inflation. In future, more sensitive telescopes might be able to detect these patterns and tell us whether our universe is a one-time event or just the latest in an infinite series. Number 6, a mirror world balances our own. One of the fundamental symmetries in physics is called CPT symmetry. It stands for charge, parity, and time. It states that if you take any physical process and you flip the charge of all the particles involved, e.g. from positive to negative, flip their spatial coordinates like looking in a mirror, a parity inversion, and run the process backwards in time, the new process should also be a valid, possible physical process. CPT symmetry is a cornerstone of our current understanding of particle physics, the Standard Model. In 2018, physicists Latham Boyle, Kieran Finn, and Neil Turok took this symmetry and applied it to the entire universe. They proposed the existence of an anti-universe, a mirror image of our own, extending backwards in time from the Big Bang. This is the CPT symmetric universe, or the mirror universe. According to this model, the Big Bang was not the beginning of time. It was a singular point in the middle of a much larger reality. Our universe, which is expanding forward in time and is filled mostly with matter, is perfectly balanced by a mirror universe that is contracting backwards in time and is filled mostly with antimatter. The two universes are a perfect CPT reflection of each other. The total stuff of this combined reality is perfectly simple and symmetric. This elegant idea has a powerful consequence. It provides a natural explanation for dark matter. The model predicts the existence of a very heavy, stable type of right-handed neutrino. Neutrinos in our universe are all left-handed, a property related to their spin. The existence of a right-handed partner has been theorized for a long time. In the CPT symmetric model, these heavy right-handed neutrinos would have been produced in the very early universe. They would interact very weakly with other matter, primarily through gravity, and they would have the right properties to account for all the dark matter that astronomers observe holding galaxies together. The model makes a specific prediction for the mass of this particle, which future experiments might be able to test. So when we look up at the night sky and see the gravitational effects of dark matter, we might be seeing the influence of a particle that is a citizen of this mirror reality. This parallel universe is not in another place. It is co-located with ours, but it is evolving in the opposite direction in time, a perfect reflection of our own existence. The Big Bang was the moment when the mirror was created, with two images speeding away from it in opposite temporal directions. Number 5, our reality is woven from deeper dimensions. While brain theory places our universe on a 3D surface, other theories stemming from string theory explore the nature of the extra dimensions themselves. The idea that reality has more than 3 spatial dimensions dates back to the 1920s with the Kaluza-Klein theory, which tried to unify gravity and electromagnetism by postulating a tiny, curled-up 4th spatial dimension at every point in space. String theory revived and expanded this idea, requiring 6 or 7 extra spatial dimensions for the math to be consistent. This is the higher dimensional multiverse. In most string theory models, these extra dimensions are compactified, meaning they are curled up into incredibly small, complex shapes, far too small for us to ever perceive directly. The specific shape of these extra dimensions is crucial. It determines the fundamental constants of nature, the types of particles that can exist, and the forces that govern them in our 3D universe. The geometry of the hidden dimensions dictates the physics we see. The problem is that string theory doesn't predict a single, unique shape for these extra dimensions. Instead, it allows for a colossal number of possible shapes described by complex mathematical objects called Calabi-Yau manifolds. The estimated number of these possible solutions is 10 to the power of 500. This is known as the string theory landscape. Each of these possible shapes for the extra dimensions corresponds to a different vacuum state, a different set of physical laws. Each one represents a potential parallel universe. This creates a multiverse similar to the bubble universe concept, but with a specific origin for the differing laws of physics. The eternal inflation of the metaverse could create bubbles, and as each bubble cools, its extra dimensions settle into one of the 10 to the power of 500 possible stable configurations. Our universe is just one of these bubble universes with its extra dimensions curled up in the specific way that gives rise to our particular physics. Other universes would have their extra dimensions curled up differently, resulting in wildly different physical laws. A universe with 4 large spatial dimensions, or a universe with a different set of fundamental particles. The sheer number of possibilities in the string theory landscape is so vast that it almost guarantees that a universe with our specific life-friendly properties would exist somewhere. It is another version of the anthropic principle. We live in a universe with our specific Calabi-Yau manifold shape because it is one of the few that allows for our existence. The other parallel universes corresponding to the other possible geometries are out there, each a unique expression of the underlying higher dimensional reality. Number 4, universes flicker in and out of existence constantly. At the smallest scales of reality, the Planck scale, which is a trillionth of the size of a proton, space-time is not smooth and continuous. Quantum mechanics predicts that it is a chaotic, roiling sea of energy. Tiny fluctuations can cause space to warp and bend violently. This is the concept of quantum foam, a term coined by John Wheeler in 1955. In this foam, tiny virtual particles pop in and out of existence for fleeting moments, borrowing energy from the vacuum before disappearing again. The quantum foam multiverse theory suggests that it's not just particles that can pop into existence. It's entire baby universes. In the extreme conditions of the quantum foam, a tiny bubble of space-time could fluctuate into existence, expand for a brief moment, and then collapse back into the foam. Most of these universes would be microscopic and would exist for less than a trillionth of a second. They would be unstable and vanish almost immediately. However, it is possible that a rare fluctuation could be large enough to run away. If a baby universe fluctuates into existence and manages to undergo a brief period of inflation, it could grow to a macroscopic size and become a self-sustaining, independent universe like our own. Our Big Bang might have been one such lucky fluctuation that survived and grew. This creates a multiverse where new universes are constantly being born and dying at the subatomic level, everywhere in our own space-time. It's a frothy, bubbling reality where universes are as common as virtual particles. Most are failures, but an infinite number of them could be successes. This idea is deeply connected to the concept of wormholes. A wormhole is a theoretical tunnel through space-time. Some physicists, including Stephen Hawking, have suggested that the quantum foam is riddled with microscopic wormholes connecting different points in space and time. It's also possible that these wormholes could connect our universe to these other fleeting baby universes that exist within the foam. This is a multiverse that is not far away in space or time, but is interwoven with our own reality at its most fundamental level. The fabric of our universe, at its smallest scale, might be a gateway to countless other realities that are constantly flickering in and out of being. It's a chaotic, dynamic vision of the cosmos where creation is not a single event, but an ongoing microscopic process. Number 3, there is only one electron in the entire universe. In the spring of 1940, physicist John Archibald Wheeler received a phone call from his brilliant graduate student, Richard Feynman. Feynman had an idea, a wild, incredible idea. He proposed that the reason all electrons in the universe are identical, with the exact same mass and charge, is because they are all the same single electron. This is the foundation of the one-electron universe theory. The idea is based on our understanding of antimatter. A positron, the antimatter counterpart of an electron, has the same mass as an electron but an opposite positive charge. Feynman realized that a positron could be mathematically described as an electron that is moving backwards in time. So he proposed that the single electron is on a journey, zipping back and forth through time. When it moves forward in time, we observe it as an electron. When it zigs backwards in time, we observe it as a positron. The world line of this single electron would be an incredibly tangled knot, weaving through all of space and time. It would pass through the time of the Big Bang, travel forward to the present day, interact with particles, then turn around and travel back to the past, then forward again. Every electron you have ever encountered in the atoms of your body, in the electricity powering your lights, is a snapshot of this one single particle on its epic, time-traveling journey. Every positron in the universe is the same particle on a segment of its journey that is pointed towards the past. Wheeler was fascinated, but pointed out a flaw. If this were true, there should be an equal number of electrons and positrons in the universe, as every forward-moving segment must be balanced by a backward-moving one. But our universe is overwhelmingly dominated by matter electrons and has very little antimatter positrons. Feynman reportedly replied, well, maybe the positrons are hiding somewhere. The problem of matter-antimatter asymmetry remains one of the biggest unsolved mysteries in physics, and it's a major hurdle for this theory. Despite this, the one-electron universe is a compelling form of a temporal parallel universe. The parallel aspect is not about separate spaces, but about the multiple existences of the same entity at different points in the same timeline. The electron is effectively in a superposition of all locations and all times, and its world line is the path that connects all these appearances. It suggests a radically different and deeply interconnected reality where the fundamental building blocks of our world are not a multitude of separate objects, but multiple manifestations of a single time-traveling entity. Number 2, the universe itself is a thinking machine. Is the universe a computer? This is a question explored by the theory of digital physics. It is different from the simulation hypothesis. The simulation hypothesis says our universe is a program running on a computer in another higher reality. And digital physics proposes that the universe is the computer. Its fundamental components are not particles or strings, but bits of information. Reality is not simulated, it is computed. Pioneers like Konrad Zuse, a German computer scientist in the 1940s, and later physicists like Edward Fredkin and Stephen Wolfram have championed this idea. The core concept is that all the continuous analog-seeming properties of the universe, like space, time, and energy, are actually discrete and finite at their most fundamental level. They are made of indivisible units like, pixels on a screen. The laws of physics are not equations describing fields, but are the algorithm that processes this information from one moment to the next. The universe is a giant cellular automaton, a grid of cells that update their state based on a simple set of rules that depend on the state of their neighbors. This idea has some intriguing support. There is a maximum amount of information that can be stored in a given region of space known as the Bekenstein bound. This suggests that information is physical and finite. The behavior of particles in quantum mechanics, with their discrete energy levels and probabilistic nature, looks a lot like a computational process. If the universe is a computation, then what does that mean for parallel universes? It could mean several things. The computation could be running on a quantum computer. A quantum computer, by its nature, explores many possible computational paths simultaneously in a superposition. These parallel computational paths could be interpreted as the parallel universes of the many worlds interpretation. The splitting of the universe is just the computer exploring different branches of the calculation. Alternatively, the algorithm governing our universe might not be the only one possible. There could be other cosmic computers, other universes running completely different algorithms resulting in different laws of physics. This is a digital version of the level the fourth mathematical universe. Each possible computer program that can run constitutes its own universe. This perspective changes our view of reality. The universe is not a static stage where events unfold. It is an active, ongoing process of information processing. Every interaction between particles is a calculation. The passage of time is the ticking of the cosmic clock, the progression from one computational step to the next. We are patterns of information being processed by this grand cosmic machine. Number one, fictional worlds are as real as our own. What is a universe? It is a set of objects and the rules that govern their interactions. This is the definition we use for our own physical reality, but it is also a perfect definition for the world described in a work of fiction. The world of a novel, for instance, has characters, objects, and a plot with a certain internal logic rules. This leads to a strange and provocative idea, the fictional realism multiverse. This idea is most closely associated with philosopher David Lewis's theory of modal realism, proposed in his 1986 book on the plurality of worlds. Lewis argued that for every way the world could be, there is a world that is that way. He wasn't just talking about small variations of our own world. He meant every possible world. This includes worlds where the laws of physics are different, and even worlds where logic itself seems to operate differently. The extension to fictional worlds is a natural next step. If every possible world exists, then any self-consistent story that can be told describes a world that is just as real as our own. Our universe is simply one very large, very complex story with a consistent set of rules we call physics. Another universe might be the one described in a fantasy epic with its own set of rules we would call magic. These other worlds are not physically accessible to us. They are causally isolated. We cannot travel to them, and they cannot influence us. In this view, they are not less real than our own universe. They are just different. Our universe has no special status. It is not the true reality from which all others are mere fictions. It is just one book in an infinite library of all possible books. This is a philosophical concept, not a scientific one, because it is inherently untestable. There's no experiment we could perform to prove or disprove the existence of a causally isolated universe based on the rules of a story. But it challenges our intuitive sense of what it means for something to be real. It suggests that reality is not limited to what we can touch and measure. It encompasses the entire space of possibility, the set of all things that can be described without contradiction. In this ultimate multiverse, every myth, every story, every dream, every what-if scenario corresponds to a genuine, concrete reality. The act of creation, of writing a story or imagining a world, is not an act of invention. It is an act of discovery. The author is not making something up. They are describing a place that already exists somewhere in the vast, limitless expanse of what is possible.